Okay, thank you, Tam. I'm going to talk about the Q learning agent, which runs in the stochastic environment. So now I have started the agent, and initially there are like 800 training episodes, and in each episode, the agent goes from any random state that you can see towards the goal state. So until it reaches the goal state, the episode is not over, and I'm going to talk about some fundamentals of Q-learning while this training is going on. So the update function, which is the most important part of Q-learning, is based on updating each of the Q values for each of the states. Now, these states are represented as waypoints, and because it's a stochastic environment, there's a certain probability related with the transition, which is defined as the transition function. So the transition function for this environment is such that with 60% probability, the agent will execute the action that it takes. But with 10% probability, it can go to either of the other three directions or stay in its own place. So the total percentage comes out to be 100%. Now the update function, what it does is uh, it uh, so we first get an action based on the epsilon greedy method for exploration. The epsilon greedy approach essentially takes a value of epsilon, which in this case has been set to 0.8, which means that 80% of the times the agent will take any random action, while the other 20% of the times it will try to exploit from the already given Q values. So the update function, now how it works is that for a given state, the agent performs an action based on the epsilon greedy approach. And after performing that action, it gets a reward. The reward function is that if the agent reaches the goal state, it gets a reward of plus 100. Otherwise, for any other state, it gets a reward of minus 1. Now, when the agent chooses the action, it moves in that particular direction by 60 pixels. So after that, it gets its corresponding reward. Upon getting the reward, it has to update the Q value for the state that it was present in. So the update function is essentially to multiply the Q value of the state with 1 minus alpha, where alpha is the learning rate, and add to it alpha times the reward plus the Q value of the state, that the highest possible Q value of the state it reaches, multiplied by a discount factor. Now this discount factor is used in order to ensure that the agent uh, takes the highest possible reward initially. So uh, it means that as the time progresses, the rewards lose some of their value. So it's better to take a reward immediately rather than in the end. So this is essentially what this Q agent is doing. And during this training example, all it is doing is it is choosing an action based on the epsilon greedy policy, performing that action and getting a reward, and then updating its Q value table. This Q value table you can see for all the states or waypoints, and it shows the Q value for all the four directions: up, down, left, and right. So this is the training phase, and as the training is for like 800 examples, so uh, I'm going to pause the video and resume it once the training is complete. And so the agent has finished training, and now it is testing. So upon learning the Q values, the agent performs the action. Now the environment is stochastic in nature, therefore for each action you might be seeing the agent to be wobbling about, but essentially because of the stochasticity, the agent, whatever action it intends to take, it might fail to take that action. Also, one thing I like to say is that uh, in this case, the agent might seem to be occupying one complete square, but we we can consider the agent to be exactly of 1 pixel size. So that pixel which the agent represents is essentially where the agent is, but the outside boundary of the agent prevents it from going into the walls. So you might be seeing that this is that the agent does not enter the wall, and therefore this line will always remain at least this much distance away from any of the obstacle or from the edge of the screen. So if we look at the Q values, we'll see that the agent is performing the optimal action. So if I start from the start state, you'll see that the most optimal action is to go up, and it does that till here. But in this state, the most optimal option was to go right, and so it went right. And here again, because of the Q learning, what happens is that it goes right, but it eventually has to go up. So the Q learning, in fact, learns that because the agent cannot move anymore to this side, it negates that and it moves up because the waypoint is actually set according to the square. So in this waypoint section, it knows that there are no further values and it changes its trajectory. And so if we track all the Q values even in any other state, it will show us that the most optimal value is towards the goal. So now we see our agent to be moving towards the goal, and currently it is in this state, and we can see that the stochastic nature of the environment sometimes make the agent slow, while at times it is moving at a much faster pace. And if we notice that's because mostly at the boundary it will take the most optimal value. In this case it was up, but at times it might just enter some other field. And this is the first policy that the agent executes. And using the same Q table which we obtained after our training, we can test again from a different start location. In this case, it is 0, 0. The previous one was 9, 0. And we see that the agent performs optimally even when starting from a different state. And for this table to be so consistent with the transition function, we had to perform 800 training examples so that the agent could learn the optimal values, the optimal Q values for each